so while I'm trying to find these files, here's what we have for the exam prep stuff. I was here last night, and trying to organize some of this stuff, but I didn't get done everything that I wanted to. So I guess we'll just access those files. But I want to point out that I have the exam prep by topic. So I think I did this before. We're covering for this exam, we're doing the ME470, some amount of ME470 stuff, so I want to make sure we look at some of that just to get an idea of what the expectations are. We do welds, springs, and bearings. Wow, I didn't mean to do that, to do 9, 10, and 11, but I did. It just occurred to me that I did 9, 10, 11. I used to teach the book in order instead of something that was relevant to the topic, but I decided to make the focus, and then I rearranged everything. Almost kind of want to keep going. Just go down to, we don't want to do 12 because that's lubrication, fluid bearings. But anyway. So here we go, exam prep material. I had it organized by way of the old exams. So instead, I have grouped them by, all right, so here, brakes, bolts, springs, welds, ME470 content, and bearings. There should be a gears one in there, so I'm missing the gears. And I lumped the two chapters of gears together into one thing, but I got to remember to put those back in there. So if you come to this right here, I have these are practice problems I used to give out. The same ones from ME470 right up to here, but these are ones I actually have asked before in ME, starting at this point, with ones I've actually asked from on ME470 exams. So we want to cover these or something like these. There's not many, there's only 2 of them really. So I haven't done it quite a while. In spring of 19 and fall of 18, I asked questions along these lines. But this is really a lot like this crankshaft one right here, so I don't know if that's fair to start asking what we just have a homework for it that I haven't even posted yet to put on the thing. But just giving a tour guide right now of what's available. And then so we have welds right here. And here are old exam problems from the Coast Guard Academy. And then starting right here are 2 at least one exam problem that I have asked before. Now, a lot of times the welding when I got to the end of the semester, so it was on the final exam kind of thing. But there's one that is a problem that I've asked before. I tried to add some stuff to it. I thought the old Coast Guard Academy ones were quite enough, so as I'm going through, I'm trying to add a couple into the thing, so holding back some but giving out some others. So we have springs, which is something we've done recently, and so here are old problems. Anything before anything like F15 was back, F14 was back at the Coast Guard Academy, F13 and S13 is one out there, but also, did I not put any in there? I thought I put a spring. Oh, here it is on the, just one question. I added one back in there that was a more recent one. I think that kind of because I've changed the way that I write questions and how long and that kind of thing, and tried to adjust. And so I wanted to add at least some that were kind of closer to what an exam problem is, because I encourage people to, when preparing, I don't want to use the S word for study. I want you to solve some problems and stuff. It's a simulating an exam, so I want to give an exam problem. So I'm going to hold off and test yourself with that, but also try some of these out. I also have the book ones that, as I mentioned up above. I think I meant to show you this right here, but I'll continue with the last one here for the bearings that I don't see. There it is. Okay. So we're doing the springs, welds, and bearings. And so here's some, and as, okay, is this all I have? I thought I had a couple more, right up here. I guess that's just what I had for the old one at the Coast Guard Academy. And then here's 2 for more recent. So spring of 20, so 4 years ago when the pandemic hit. That was not a great semester. And there's F19, and boy, they're very similar to each other. So you can just get a sense of some example problems. things you can expect on the exam. Something around this level of difficulty. There is a couple examples.
3 problems? Or
probably 4.
4.
Either 3 or 4. It'd be the ME470 thing, maybe. Don't know for sure. I haven't read it yet, so when I read it, I'll know. Just don't need to be coy, but I just don't know. I also have to, when I write it, I take it and see what the time is, and then go,
and it's just like typical
thing. Yeah. My typical modus operandi. There is a couple bearing problems that were like, that's a kind of a good problem, and it's not like these problems where it's like this conceptual thing. I don't know if those are fair or not, but I don't know. I'm not trying to trick you into things, obviously. Trick you in exams. I'm trying to measure your mastery of the material, so I probably wouldn't ask that, but if you go through some of the videos. And so I've also moved, the videos are going to be hard to find the problems. I was thinking I was going to rearrange these links and actually do one of the YouTube link to the exact time where it was in for the exam. But that was like way too ambitious. I thought I'd have more time. I don't know where the time is going. It's going to get worse too. I don't know. But that's me here. And then lastly, this is, but not to. Just to say, the previous professor teaching this course, this is all you got throughout the semester, this right here, and then you had an exam, right? And didn't give, you had answers but not solutions to these things right here. I'm not trying to get credit for that, but I tell you, it is a way to approach it, and you got to really learn it. You got to really do it on your own, right? When having that there, but it is effective. It could be time consuming, and people who are really into putting that effort in can really fall by the wayside. So that's why I don't like to do it. But anyway, I also, because you don't necessarily have the 10th edition, and I gave the problem numbers, and they're not the same in every edition. I went ahead and put them in here, and put them in the order of the chapters, right? So here are the problems that those numbers are referring to. Here are the answers, and yeah, okay, so I think I only put the answers in there, but I also put the answers that I put up here, I put in between numbers. So there's not just the answers, it's like you would get, here's a number that you would calculate midway through towards the answer to see, hey, okay, I'm on the right track kind of thing. And I think maybe going through some of these might be the good use of our time. So there's the springs. No, I think what did I start? I think I just lied to you. I think it was bolts. Yeah, bolts. So that was chapter 8. So we're here about chapter 9, which is the welds. Chapter 10, which is the springs. Chapter 11, which is which are the bearings. And one of these questions in here would always mess me up in the head. Which is the conceptual problem. I can't remember which one. I'm going to guess it's probably like 11.3 or something like that. That's one. You'll see me sputtering on in one of the exam review sessions where I was like, what? And as I'm trying to figure it out loud, it's not my favorite thing to do, is to show my soft, weak underbelly of I don't know how to do all these, especially not live. I like to sit in my office staring at stuff, thinking really hard and trying things out and avoiding even knocking while I'm in the midst of it, so I can don't go to cardiac arrest.
Any obnoxious ringtones in the background?
I bought some Bose noise canceling headphones, and I should have checked. I asked for them for Christmas, and I thought, well, I was going to find out the model that Jack Breton, which we probably don't know, was one of my students, and he works at Bose. And some LinkedIn thing said they just launched a thing that we helped design, the noise canceling headphones. So I'm just going to pretend but of course I didn't now. Pretend like those are the Bose noise canceling headphones. They've already got it. But they really are pretty good with that, right? So, anyway, okay. So there's the rest of the thing we don't need to. Let's get into it. Too much preliminary stuff. What do you want to see? Got requests? A particular problem, a category of problems, just say free for all, spin the wheel. Should have brought the wheel.
A weldment with torsional.
Was that?
A weldment with torsional, like the
A
Canada.
weldment with torsional. Okay.
What were you gonna say? I just said it.
Okay, let's go. Let's go to the camera. Someone in my mechanisms class was giving me grief about my how often my hand was getting in the way of dealing with certain problems. I guess I can kind of understand that. There's a lot of compass action involved right there, right? Going on top of everything. All right, let's take a look. I could open up my book right here and find it, but I'll be flipping around. That's chapter 9. Number 9. Flippy. What an exciting class of flipping pages. I was here till midnight last night, so I got home at 1. And she didn't notice. She just leave. And then she was still in bed when I left. So there you go, sleepyhead. Well, here's an interesting one. I didn't ask for that. So we'll do the heavy lifting thing. And, here, look at one of the things, weld symbols. Got to know what the basic ones, not the crazy ones, but the ones that we've been doing, like, okay, what does that mean?
That one's all around.
Yeah. This is the lazy man thing. I liked me some all around. And a lot less symbols. Just weld it all over the place. Also, on ships, we don't want to have the little gaps where moisture can get in that you can't chip away the rust, because everything rusts on day 1 before the ship even leaves. So let's see. Let's pick one of these guys. Picking the hard question, but I don't have the answer. I don't have. You know what's good? Old school. Tell you what. I know you guys are juniors, so it's not. It's like too late, right? Man, you use this thing in the back of the book. I tell you what, this is how I made A's in college. Yeah, I know. So pick those and find the one. No, when you're solving something, have a target. It's good to have a target. And so what is this? It's somewhere in between 29 and 32. 29 and 32.
What is their reasoning behind 159, 14?
I don't know.
I got lazy.
Lazy?
Like, these ones are good.
Yeah. So, did we have one in there? My brain's not working. No.
29 through 32, no.
Well, that's a son of a bitch. Why would they do that? Why you gotta be like that? Jerks. They hate us. They hate us. Well, I guess maybe I'll try to figure out a way to remote into my office and do this one. All right. Let's go 32. Maybe it's the most interesting one. Did they already give us the allowable stress on here? I don't like the ones where you had to find out the F, but we could do it anyway. So we can find out what the maximum allowable force is going to be given this amount of stress, which we could also pick ourselves, right? But here, we'll just do this one. Yeah. So let me write down. Maybe even need a straight edge. The more advanced straight edge. Yeah. And that's the right here, and then we have an H. And interesting, kind of interesting, 45 degrees. I don't like 45 degrees. B, C, D. There's something against A. There's H. So let's see. B is 4 inches. C is 6 inches. D is 2 inches. H is 5/16. And this they could have told us also the thicknesses of these, and then we would have to look this up.
Sorry, what does the triangle mean again?
It means a fillet.
Yeah. Okay. All right, this one.
This guy right here, I didn't copy very well. Usually we would put a little message like,
so it's fill it all the way around.
Hi.
So it's fill it all the way around.
Fill it all the way around.
When there are two triangles mirrored,
it won't have this circle all the way around. It wouldn't that way. It would just mean that would be on this side and on this side. If there wasn't a circle right here, this would oddly mean on this side. I've often thought that should mean on that side. Would make more sense to me. But if it's on the top, it means on the opposite side from the arrow.
It's almost like the leader line should be pointed at the bottom too.
I guess so. Yeah.
Can you go down to the example below that? So the two triangles are just top and bottom.
Yep, just top and bottom, and then a third.
Yeah. So why wouldn't that just be all around?
Because it's not on the back side of that.
Yeah. Okay. All right.
If it had the top triangle right here, that would have been a little weird. But I think you would have been able to figure it out. It's only one kind of thing for the thing, but yeah.
Just on like a mirror.
Yeah, this is just making a C.
Yeah. Okay.
Yeah. It's a good question because we didn't mention it. So we want to find and then tau allow. I like how it kind of rhymes. Tau allow. 25 KSI. And then find F. Okay, so two things going on here. So we're going to have a little bit of a combined stress type of thing, which is good. We're going to have a three-way combined stress. Ooh, that's interesting. So we're going to have three types of stress. We could call them primary, secondary, and tertiary. Great word, if you wanted to. The three things, we usually consider the primary as the direct shear. That's the downward thing that's trying to make this guy, if that was the thing, it's making it try to slide downwards, right? Boom, because it's going down. We also have the torsional one, which we would probably consider that the secondary. And a little bit of weirdness, we have the one that's going to have a component going that way, so we're also going to try to slide it that way. And those are perpendicular to each other. Now, I have a little bit of heartburn with the, I don't mind kind of the idea of it, but I got a little heartburn in the fact that if you zoom in and you tried to reconcile the directions of these on a little stress element, you'd get your mind twisted. And I don't know if I could really agree with the concept of the thing, because we're talking about all shear, right? And that's a lot of that's because we're looking at like a plane that kind of like goes diagonally. We're going to assume it's 45 degrees diagonally through the weld, right? So when we're joining two materials right here, we have a weld that's like that right there. And our idea is that there's going to be a shear plane that cuts right through there, that we assume that's where the shearing is going to take place. And now we're going to do that 3 separate times for this at like the worst location. And then we're going to pretend like those 3 are perpendicular to each other. And I just can't get my head wrapped around how that could be. So we're just going to hit the accept button. And that what we're doing here is overly cautious, right? But weird, strange to me as well is when you do the FEA with the thing, when it says that you're underneath this allowable, you get like really, really high stuff. And a lot of that's because of the stress concentration going on right there. But we're going to go ahead and proceed through this procedure knowingly turning our brains off. So at least we know that we're turning our brains off. And what we're essentially going to try to do is that we're going to say that the total stress is going to be tau prime squared, or I should really give these subscripts because these primes are going to drive us nuts. So let me go this right here. Here's going to be the, I'm going to call it DS for direct shear. Maybe I'll write that over, direct shear. Plus tau torque. So that's going to be the torsional one that's going about the center of this, because this thing is going, Oh, I just realized we could have. There's an aha moment. We got to draw ourselves an FBD, otherwise we would be missing something. Easily missed thing going into. I was about to be a violet. Did you notice where they put that force right there? Well, let me go back. We'll see that in a second. And then, but here's the plus. So they're saying these are all three are going to be perpendicular to each other. Let me wait. 1 second. Let's hold off on this. I told you a wrong thing. Like, this is tough to do live, right? You're hearing me. My inner thought. Nobody wants to hear these, but my thought processes as I'm going through these right there. Let me take a step back through what I just said and think about it. All right. So let me get the moment, which should be a torque that we're placing onto the thing with the free body diagram. And here's my dash right there onto this thing, my FBD, and I have a force. If I have a force like this, it makes sense to make it into components. So we'll go Fx and Fy, something that we don't know what that is right there. So we could write over to the side that Fx is equal to F times the cosine of 45. I guess I'll leave it like that. Fy is equal to F sine of 45. We want to get this is going to be, if this was a C instead of a rectangle, we would want to make sure, and maybe it's a good procedure anyway, when you're doing a problem, to go ahead and look up into this section right here, and look up the thing that we're going to use, which is going to be a rectangle. If it was a C, we would want to definitely reference. It's not going to be too terribly difficult to figure this out on our own, where the X location would be to get to the center of the thing. But it's kind of obvious when it's a rectangle that we're going to have it this distance right in here. So I'm hedging because I'm calling it a free body diagram. Equivalent. Equivalent load diagram. So we're trying to find the moment, aka torque, that we get because of these two right here. So that we need that for our for the torsion equation right here, this equivalent moment. Let me go. The equivalent moment. This is not the reaction moment. This is the moment that's created by these two forces. So what's a little interesting here is we have this distance, which is C, and we have this distance, which is B. So what we would have is the moment arm is going to be Fy times C plus B over 2. Here's the interesting, this, we could just stop right here, and I think this might be kind of preferred, like a better thing to do, because we're about to subtract. You notice that this is creating a clockwise moment, this Fy. Note that Fx, though, has a counterclockwise moment. If they had not put it right, if they had not put that 45 thing down here at this bottom corner, that wouldn't be something to recognize. But it's almost like a little trap. But maybe when we see I don't know if we'll see, but if we do see the solution manual. Maybe they just ignore it because it does make the thing less, and so maybe it's good to, and maybe it's not a large amount because D is kind of small right in there. Because we're trying to find F, it's probably in our best interest to work all of these things out and come up with a single number to put against there, just to make life a little bit easier so we don't have to carry around all of this, all these values. So C is 6, and B is 4 over 2, and this is F cosine 45, and D is 2 over 2. So we can get what the equivalent is going to be. So 6 plus 2, I could have done that in my head. Kind of silly. Sine, I know, I could have. And then minus the cosine of 45. 45 cosine minus. So what we're left with is like 4.95, really, times F. And while we're going through this thing, I'm gonna put a pin in our trying to combine them here for a second, so we can. I think after we get to this, it'll be a little easier to do. Let's go ahead and get what the stresses are, the torsional, right? So we're working on the torsional here, and so we will pick up. While we're here on this table, I'll write down these things that are on the table. So we got the table 9.1. A is going to be, it's a rectangle, this guy. So we'll write the 1.414H. And this is always messed up. These are using B's and D's and stuff right here, but our problem has B's and D's, so you want to kind of be really careful. And it's almost like a little test. Can you concentrate enough to match up the non-same variables that they're overlapping with the thing? I don't know. Can I pass the test? We'll see. It might be best to just not be writing it down. Do it as quickly as possible here and substitute them. We know H is 5/16, which I could pretend to like I know what that is. Is it 0.3125? It's like a little test. 5/16. Look at that. Yeah. If I got it wrong, I would have been. That was just a crapshoot. There's no way to know. All right. So in this figure, B is the width right up here. Oh, and look at that. They were nice enough to make those the same. I actually, I guess maybe I'm a cynic, pessimist in my life. Many people reusing the same variables right next to each other. I've become jaded. That's sad. I want to be Mr. Positivity, but life doesn't seem to want to agree with me on that. So B here is the 4 inches. Yes. And D is the 2 inches. So for the A math, 1.414, boom, and 6, boom. All right. So the A is 2.651 square inches. Now the next one, we want the JU. JU is B plus D cubed over 6. I didn't even leave enough room. And we just said that the B was 4. And the D was 2 cubed divided by 6. you see me in my career keeping track of stuff. It was like the skill set I needed most, keeping track of stuff. One double check. I don't like my answer. All right, so I got 6 raised to the 3, which I should do in my head, but I can't. And then, divided by 6. So it'd be 36. Duh. Yes, 36. And these are actually inches cubed. Got to remember that's a JU. We're not done. We got one more step left. We need to take J, and let's see, where's that equation, just to remind ourselves. Be right here. Boom. You got the White House. 0.707 HJU. So 0.707. 5/16. Oh, you know that's 0.3125. Just like how I did that. Look at me, persistent me, with putting a sig fig something. 0.3125 times 0.707 times, and we have ourselves a 7.954 inches fourthed. Boom. And okay, so the torsional shear is this guy right here. I guess I'm going to go, because we have the 3, I'm not going to play with the primes. And it says MR over J. Okay, so now we have to say, well, what is R? So we generally, I think it's a good idea to not use find this one, but instead find the components of it, instead of trying to break it down into components. All right. So by this I mean that we could go torque X, and I hope I have enough room on here. Torque Y, and picture it as I'll redraw. That we're going to have here is R. And it's going to make the swastika thing. I haven't joked about it. No, it's not that I joke about it. It's just a weird thing to think of. Like, it always makes like a little swastika looking thing. At least it helps you remember it. Right? I don't know. I shouldn't even say it. But instead of finding this R that would find this magnitude, find this guy and that guy. And pick out the worst one, but it turns out it's probably going to be this. It's got the same R in each place, so you don't have to find it 4 times. You just have to kind of keep track of it. Sometimes the X and the Y, am I going to say that the right way? Yeah, it might change. So instead of using R for finding this one, we will use the M and say, I'm just going to put it in the symbols, right? Because this for us is B, so that's going to be, let me see if I can get this right. I almost got it backwards. All right, so it's going to be 1/2 of D, right? So it's going to get this one, it's actually going to be this distance right here. To get this tau torque, I meant to Q, X. And same thing here with the tau torque Y. So this one is going to be D over 2 in J, and this is going to be M. It's going to be, to create this guy right here, is going to be that distance right there. And so that's going to be B over 2, J. So what we're left with is 4.95 F. D over 2, this is going to be 2 over 2, so duh. and divided by 7.954. And the same thing true here. 4.950F. And now we're going to have, B over 2. So that's going to be 4 over 2, right? Is it B4? Before? Yeah. Do something wrong?
Yes, maybe a joke before what?
Ah, gotcha. I was going to try to make a joke, but I decided I wasn't able to. So, props for being brave. I thought I'd fall on my face. I'm not so bad. I'm okay with falling on my face. I'm kind of just wasn't using it for anything anyway. So there's on Monday, there's this dinner opportunity to use some tenure for this. It's like a celebration of all the people who are getting tenure this year, and my wife is coming, and Dean Elnajar is going to stand up and say something, and he had me write what he's going to say, and I made it all about my wife. But I thought it was pretty funny. But I just don't know if I could coach him in the timing it's necessary. Humor is important. Okay, so we have these two guys. I keep moving this thing in the wrong spot. Sorry. So the two things left to do, they're actually going to be the same value, aren't they? Because we're going to use, both are going to be V over A. It's the same area, but they're going to be in different directions. Oh, yeah, okay, yeah, that makes sense, right? Because if we're looking up here, right, I should have made this thing bigger or used, if I had more pencils. Let's only focus up on this spot. Oh, I got to make it bigger. Just to make the concept, this is not a good example of how quickly to do a problem, and I don't necessarily need. I know, but it's not that hard of a problem once you see the thing. But I'm trying to make the explanation on top of it. Okay, I was thinking about going to the next sheet of paper, but in this direction, at this spot, for here, we could call it the primary one that's due to tensions in that direction. So those components will add to each other, right? Down here, the torsion one we just found, that's going to be in the same direction as the one that's due to the direct shear that I'm saying is trying to push this thing down, right? I don't have great names for this. The vertical component of this that is making this thing shift down that way right there, it will add to right there. I think that makes this corner the worst spot, right? Because down here we're going to have, these are going to be the directions that we would get because of that torsional one right there, right? But we would still have a component in that direction due to the tension, and we would have down here. So that part of that is going to cancel out when you get the total one of the thing. So this one will definitely be bigger than that. And then you do the same idea up here. We would have, due to the torsion, we'd have that and that, which is going to be represented by that. But we would have this and that due to that force going that way and down that way. And lastly, I think you get the idea. But I can't stop myself from doing it anyway. There we go. Boom. Right there. But we have that and that to add to them. So I didn't label all of these right here. This is the word spot. They're going to be equal to each other. Let's say that it's going to be direct shear is what I called the thing before. This is we call this axial. This is going to be V over A. And they're the same because cosine and sine of 45 are the same, right? So that's the reason why they're the same. If it had been anything else beside there. So what we could do is put F times and whatever, sine of 45 and divided by A, which was 2.651. So we get 45 sine 2.651 divided, and it's smaller than those others, 0.2667 F. And now we're ready for the combination, which is limited to tau allow, can only be equal to we'll say tau direct shear plus tau torque y squared plus tau x, for lack of a better name, tau torque x squared, right? So what's that? 25,000 equals square root. And by the way, every one of these has an F inside it. Like, you know, that's F, and that's F, and they're all going to get squared and then square rooted. So that F is just going to come out. So I'm not going to write it every time, but that's okay. We're all okay why I did that? All right. If you're not, speak up. Right? It's totally fine. So in here we're going to have a 0.2667 plus, and I guess because it's not actually going to matter if I get them backwards, but I'll try to get them the right way. This is the direct shear goes with the y, so this is the 1.245 squared plus the 0.2667 plus, and this should be the other one, 0.622 squared. All right. So tedious. Tedious? Oh, no. I try not to make puns, but I do it anyway. I can't read my own handwriting. 224.2667 plus squared plus square root. All right, so all I'm going to do here now is divide 25,000 by 1.753, whatever. And I get F as 14,257 pounds. Or, don't like doing it, but 14.3 kips. I don't know if I want to take the time to see if, to compare what we did with the, compare with what the book had. We don't have the answer to it, but that's the big idea, right? The biggest idea is this right here. What I initially said was incorrect, but there are problems. The problems where we had the torque, remember, like we had the pipe where you have you have a torque, a bending moment, and an axial. I wouldn't ask that problem because it's too long, but I would ask it as a final exam problem, because if I when it had a final exam, and you had usually, I won't commit to this, but generally speaking, I have a couple required problems and then pick two out of whatever onto the thing on the final exam. I have been burned by that, not just because we have an A-bet requirements and I need to have like the same problem or a very similar problem every semester, and I forgot the gear one that I had been asking, so I kind of missed it. I had like halvesies between I like it, but now I'm going to be the coordinator of that. I just have my own rules for myself, and now I got to try to impose them on other people. No, it's not going to be pretty. But let's not worry about that. Not here. What we're here for. Let's talk about another problem, because that took way too long. Although we did have almost 15 minutes wasted in the beginning of me talking about what would be of the topics onto the thing. So it was a half hour, but that's still too long for this exam. But would not be too long for a final exam. That's what I'm saying. Maybe. If you were took at the same speed as me. All right. What kind of problem would you like to do? Spring? I almost said, do you want to do a bolt problem? That's not on the exam. I really like bolt problems. I like them. Spring. Usually, there's way too many things being asked in a lot of these spring problems. So you'll see the one that I pointed out that I was like, all right, I'll sacrifice one of my recent problems and put it into the practice problems. That's about the length of the spring problem that you can expect, because there'll be a lot of stuff right in there. So you could just ask some rando problem. Want to ask some rando problem, or do you have some type of one in mind? Random has worked for me pretty well. I'm a guy that married the girl who sat next to him in high school because of alphabetical order. Random's been pretty good to me. It's the same. Don't let Laura hear this. She'll be mad at me. My job is to make her mad at me. It's good. Where do you go? Let's see. Listed are 6 springs describing customary units and 5 springs SI. Investigate these square and ground-ended helical expressions to see if they are solid safe. If not, what is the largest free length to which they can be wound? Using NS equals 1. Okay. Here we go. So, what do you want? US units or SI? I don't know how this works. I don't even put a lot of thought into how this works. It just does what it does.
It's US because they're just
US is more confusing,
Yeah, okay. I should ask, anybody here have the international version of the book? No? Okay.
It's illegal.
It's illegal. It's immoral. It's made for developing nations. We're getting the $20 book version. McGraw-Hill's hurting. That's why they sell it for $200, $200 more. So how about 10-12? Why? Don't know. Just saw it. 10-12. And information, the D, by which they mean the wire, is 0.148. Watch this have some kind of nasty little side effect thing. Like, there are not that I need your sympathy, and nor do I think I will get it. But being a professor, a lot of times there's barriers to having a worry-free life, and some of them is like problems in the book that are screwed up. I mean, I reasonably people be angry at me for the fact that like a problem that I assign, I suddenly send out an email going, oh, wait, I didn't notice this. Damn. And yeah, it's my fault if I rip the problem. Sometimes it's the book. The solution manual's wrong. And you're like, well, that's pretty arrogant. I'm like, no, I tried it a bunch of different ways. Found a mistake. Yeah. Anyway, okay, so we got this material. We might want to find those things first. We also found that these were squared and ground-ended helical compressions. So those are things that we might want to look at to try to find the number of active coils. So either place is a good place to start, is to look up the table. We also, I should write the find just to remind ourselves so we can go through the thought process. First we asked the question, solid safe? Solid safe find if it's solid safe. And like, if not, max F using NS equals 1.2, which is to say it's a safety factor. We want to say, okay, well, let's not go beyond this amount of stress. So I think the number of active coils is probably the first thing to get into. And it's the table early on. Flop, flop, flop. We go to here and find, this is the ground, squared and ground. So you can see that we have two end coils and that the number of active coils, so you get the NT is equal to NA plus 2. Therefore, NA is going to be 5.75 minus 2, or 3.75 coils. I think so. And anything else? Oh, solid length, right? So we have solid length. LS is going to be equal to DT according to this right here. Yeah, they said it was. They said it was ground, right? Squared and ground. Okay, it's going to be equal to DNT, or 0.148 times 5.75. But it's 0.8510 inches. All right, so we can say what the deflection for solid is going to be is LO minus LS, which is 2.5 minus 0.8510. Oop. Oh, I know what I did. Big and dummy. You're such a screw up. 2.5.851. Okay. 1.649 inches amount of deflection. We did all the damage we can there. Let's go. We need to get to K, but in order to get K, we need G. So let's go find G.
It's 11.7.
Whoa. You're fast. While we're looking for materials, let's first get... Yeah, okay, so we'll go to the G first. And that is A227. So we got right there. And so that's hard drawn steel. This is the HD. So this is the right spot. We want to get the correct wire diameter. So it looks like it's greater than 0.125. Did I get? Is it 0.1? Okay. There. So we got right here. G. This is the one we want. 11.4. So I'll write down what that is here. Tab 10.5. G is 11.4 MPSI, or million. And then while we're over here, we'll get this guy from table 10.4. And they got hard drawn wire. I believe that's the right one. It's got these funny little thingies right here. I don't know what to call that. It's a double cross. Hey, that's a good name, double cross. You double crossing sidewinder. Just says surface, no. Oh, it has got the number right there, right? Look at me, not paying attention to stuff right in front of me. So we get our M, I'll write that down, 0.190, and A in US units, Is it the right one? Yeah. A is 169, and we use that to find the ultimate, so might as well do that while we're here. A over dm, and so we got 169 and 1.148 raised to the 0.190. And Mr. Calculator says...
I think the A is actually 140.
Is it?
Yeah.
My bad. See, I'd fail this exam. I just get a little couple points off for being dumb.
Such is life, right?
That was just mean, though, for being dumb. There was a funny TV show called My Name is Earl.
Classic.
Classic. And his ex-wife would use the word dummy all the time. And my sister used to say it commonly. And she admitted that her son was doing something. She says, "Big dummy." She's like, "Oh no." I just called my child a big dummy. Just because she was so used to mimicking the phrase. It's pretty funny. All right, so we got 201.3. Cast out. You big dummy. We go back to K. Which, remember, we got from Castigliano. Remember that, right? Castigliano. Remember that wonderful, fun topic. Energy methods. And you're welcome for me not making you do it. Like I did the first year I taught her. Seemed like a good idea. It falls under the category of they did it to me, so you have to have it done unto you as well, which is like the opposite. Which is the opposite of like the golden rule. Something I made a mistake. I have forgotten to do. I should have done this right away because it's easy mistake to make. Is the diameter of this big D? Big D is not the OD. Big D is OD minus the little d. Easy mistake, common mistake to make. I almost made it. Say again? No, it's the mean diameter. If you had 2D, it would be inside down. No, that's totally legitimate. Like, so if you think about it as like they're taking a shortcut. I almost want to think of it as like we have what we've done is taken the wire diameter and taken half of the wire diameter and multiplied it by 2, and then subtracted it. That kind of makes more sense, right? Yeah. As if you had the outside diameter, and then you're like, well, we want to go in 1/2 of the wire diameter on each side to get to the mean one. Totally legitimate question asked. I would, yeah, me too. .972 inches. All right, so now we're armed and dangerous with enough information here. I'm going to make this go to the 4th. G. Remember that this is millions, so I'll put my E to the 6 right in there. 8, and then we put into our number that we just got 1.972. Maybe it was better. Here's Mr. Rationalization that we waited to do this so that the impact of remembering to do it would linger more. Maybe? No. Okay, it doesn't matter. All right, so they don't say the number of active. It doesn't have an NA here, but that's what they mean. Like the reason why we said the number of active was for this.
Yeah. It does say just a few lines up.
They like to hide things. It's almost as if they want you to do an open book exam and see if you don't really know the thing, you're just throwing numbers into the thing. You would almost kind of think that's why Dr. Deal has it as a... But that would be cruel in some respects. But also, pedagogically, which is an unnecessarily long word, useful. Do you really know it, or are you just faking it? Maybe both. Oh, you're faster than me. So very fast. Jeez, speed demon. 11.46. I'm still plugged in it. Boom. See, I was busy, blah, blah, blah. It's my job description. What'd you say you got?
92.45.
Shit. I got 23.77. So I gotta tell you this, but identifying mistakes as you make them is I'm trying to rationalize. Yeah. I think, damn, do I make a lot of mistakes? Damn. Hopefully I get better at it. All right, so we were able to get that force first. We can find what force is required because we know the deflection and we know the stiffness, so we could find what force it will be placed onto the thing. So you get the F to make it solid. It's going to be equal to K times del to make it solid, or 23.77 times 1.649. 1.649. Boom. And so that should be 39.2 pounds. And now we got to find out what stress that is. And we, by the way, we wanted to. I probably was derelict in here. While we were doing this, we should have converted this into shear, right? Because this was an ultimate strength. For whatever reason, they do that. So there's always another step. And in doing that, we often will have to make a decision. And so we just note that it would have made more sense while we were in that location to have adjusted that. Let's go to the stress portion of it. We need to get the Bergstrasser. That's what we decided that we were using because there was two choices and they didn't look like one was better than the other, but the Bergstrasser had a cooler name. So that seemed like a good enough reason. So I'm gonna because we need it here, I'm gonna go ahead and calculate it here first. But note that we need the index. So we'll look at the index first, get the Bergstrasser, and then plug it into there. So the index is, remember it's D, not outside diameter, that D, so good thing we calculated it. 1.972 divided by 0.148. That ends up being, whoa, did I do that wrong? Oh, that's a large number. It's usually somewhere between 3 and 12, but it's 13.32. Interesting. That means that's a very thin wire, right? That's a large diameter compared to a small wire diameter. So that's a slinky. Well, that's just, I guess, slinkies are flat, aren't they? Is that true? Yeah. Were they always flat? I think they were always flat. So we get the Mr. Bergstrasser, whose name is cool. Maybe that's a subjective thing. I don't know. Well, I was almost about to write the wrong one down. It's this one down here. 4c plus 2 over 4c minus 3. It's very big. So 4 times 2 plus 4 times 3 minus. So once again, these aren't very big. These there was I do recall trying to figure out this combination for a problem to try to make the Bergstrasser a larger number. I guess it doesn't because they're for this. We get the tau. We call it the solid tau. Of being KB 8FD over pi d cubed 1.099 8 times 39.20 and 1.972 0.148 cubed. Okay, so 8 times 39.2 times 1.972 times pi. I would go for some pi. 0.148 cubic divided. It's not very high. I guess it is. 66,759. Anybody else? Anybody confirm, refute? Bueller? Oh, good. Okay. Just feeling better about that. So many opportunities to make a little math mistake. Need to go back and see what kind of adjustment we should make to the yielding of this. I wish it was a little bit more clear, and maybe I should read it again at some point. All right, so it starts right here, this discussion about the shear yield, that it's somewhere in between 0.35 and ultimate and 0.52 ultimate, and we're reminded right here that von Mises says it's 0.577. But that's shear yield to yield. We are talking about ultimate and shear yield, right? So little discussion thing going on. Most of the time what we just go to is I just go right down to here. Here's hardened, here's music wire, cold drawn, but we're hard drawn. Is that the same? Is cold drawn and hard drawn? They sound like they could be the same. The cold and this hard, I don't know. I should read it a little bit closer, but I think 45 is the way to go. And we have to decide, is it before the set removed or after the set removed? I think we're always doing this. It's including the Bergstrasser right in there, you note. And it says it includes that's just the shear coefficient. Bergstrasser incorporates the shear as well. but it's also about the weight. So I'm going to go with 45%. It's a decision that shear yield is 0.45 SUT, which is 0.45 times 201.3. We had from up there. And so 201.3, 0.45, boom. We have 90.59 KSI. So as a safety factor against this, we'd have SSY and tau. And I might make them, the safety factor is about solid height. So we would do 90.59 divided by 66.76. And I think we're going to be fine, 1.36. So I think it's solid safe. We could declare, therefore, solid safe. And if it weren't, we would just start going backwards and figuring out, okay, we take that. They said 1.2, so we would make it an allowable shear stress. We'd come back in here and find out what that force would be. And then from that force, we'd find out what that deflection could be. And from that deflection, we'd figure out what the length could be to be, to remain, so it was not going to yield. I know it's a long problem. I usually won't ask a problem that long. Usually.
I don't know why, but whenever I punch in the K, I always get 46.5.
This K?
Yeah.
Okay.
Yeah,
It could be. I don't know. 0.148. All right, and then 11.4E6. Boom. Dividing it by 8. Okay, cool. That's good. Well, it's good. Anytime that you can find where you're making an error, it's another opportunity to, I don't know what the words I would say next time. Okay, cool. No, they let me know though. All right, feeling good about springs. We pretty much got everything. The only thing else, I probably won't ask it. So, but no, I'm probably sure I won't ask it. I do enjoy the natural frequency portions of the things. Unfortunately, I'm not sure I agree with their method of finding that frequency. There's something going on there. In terms of its first principles, it should be 1 over 2 pi, right? Or yeah, I think so. Yeah, because we need to divide out the radians. Usually, circular frequency is square root of k over m, right? Which gives you radians per second, and you need to turn it into cycles per second. And there's 2 pi radians per cycle, so you need to divide by 1, but they only divide by 1/2. Where does the pi go? I want my pi. So my guess is that they are also doing something to attribute the mass, that the distribution of mass, which is not, some of it's near the end where it doesn't matter. If it was a single mass in the middle of the spring, then yes, but we have a distributed mass across the whole thing, and my way of thinking it, the ones that get near the end, they don't do a whole hell of a lot, that mass. the ones in the middle that matter. So maybe that's where, I don't know. It just seems like a weird thing to me. All right, so far we haven't done a bearing problem. Is that true? I think it is true. Man, you do not have a good desk. That is not a. That's already got. It's pre-sloped. Yeah. And the wrong level. Look at him though.
These things just need to be thrown into a fire.
Yeah. That's pretty blunt.
Whoever approved these chairs does things.
Oh.
No,
or was not an engineering student. Yeah.
Freaking references.
This is the kind of desk that you only use when you're using only a blue book. In 5th grade. All right. Well, boy, this is really rolling the dice here. I'm afraid. Yeah, see, I think it's like 11-9. That looks like the kind that really messed me up. Like two ball bearings from different manufacturers are being considered for a certain application. Bearing A has a catalog rating of 2 kilonewtons based on a catalog rating system of 3,000 hours at 500 RPM. Bearing B has a catalog rating of 7 kilonewtons based on a catalog rating at 1 million cycles. For a given application, determine which bearing can carry the larger load. I've done that problem a bunch of times. It requires you to think. Yeah, well, we should work on that. Or you should change your attitude, and you are good at that, and you just have to just believe. Hit the believe button. It's all state of mind. Isn't that what we learned from the Wizard of Oz? Isn't that how the Scarecrow got his brain? He just got a medal or something for being. Well, that was the. I don't know. Did you know? All right, I really enjoy tangents about the Wizard of Oz. I personally hate it. It's terrible. It's not a good story. It's not. There's no redeeming quality of this story whatsoever. What's the moral? What's the whole? You know why? Because it's a political allegory about getting us off of the gold standard. It's lampooning a bunch of politicians that we don't even remember anymore, who are all about follow the yellow brick road. And the Wizard of Oz, Oz stands for ounce. And they weren't ruby slippers in the book; they were silver slippers. And it was like, silver's the way. That every person represents a certain group of the American public. And Dorothy is this naive Midwesterner that's being tricked down. That industry was the Tin Man, and the farmers who the Scarecrow, and there was a politician who resembled the Cowardly Lion, and there you go. There's the Wizard of Oz for you. Explain it. Totally messed with your mind, huh? Not a good story.
Yeah, but it syncs up with Dark Side of the Moon. So
it does sync up with Dark Side of the Moon, and if you gotta get the list though, because he goes, and which is which and who is who, and he looks back and she looks back between the witches.
And she falls off the fence.
Oh, the little bells saying when she's riding the bicycle. If you don't know what we're talking about, sorry, apologies. Have I? Yeah, I'm running out of stuff, man. I tell you what. You hear Lori? She's so sick of my shit. She's not actually. It's kind of funny. Same repetition. All right, so we have the manufacturer. I'm going to do this problem. I don't like it, but I'm going to do this problem. So we're going to think our way through it. Has a catalog rating. So let's say we're going to go C10A is equal to 2 kilonewtons. And their system has a Laverne A of 3,000 hours. And at NA equal to 500 RPM. Whereas manufacturer B has a catalog rating C10B of 7 kilonewtons. And they use L R, let's go, I guess I could have just made it C, of 1 million. I'm going to find which can carry larger load. How do you think you approach that? Sure. You have a choice. You got to make one match the other. This is an apples to apples comparison. How do you go about doing the apples to apples? Well, you can either convert one so it's the same base as the other, or convert the other to the same basis of the former. So you do it both ways, right? So let's say we want to convert this one to this one. We go C10A is equal to FD times XD to the 1 over, and I should have, I got to give it some kind of name onto the thing. Let me go, I don't know how, I'll just leave it as D. And this I'll go as A. I don't know. So, using, I'm starting to lose my head here. Okay, so I'll make it. I need some food soon, or bad things will happen. So I'm told this right here. I'm told this is 2, and we have FD, and our situation here to get this into cycle. This guy, we take 3,000 hours. I just confused myself. I'll get it back just a second. Yeah, I could do this. Now I've just figured out a third way to do this problem, and that's always confusing. It's 500 times 60. I apologize. I'm trying to decide if I want to put this here or this here right here. Let me take a second to think. We have a catalog rating here, and I want to find this. I want to find out what force can be used with this catalog rating. Yeah, okay, so if I were to convert this setup, this is how I would do it. I would go to the 1E6. Yep, this is correct. Okay. I just wanted to try to make sure that I was doing this the right way. I could put this in I could have swapped these things out. What I will find with my FD is that this will because this thing on the top right here would have converted this into this, but so now it's onto here, it would convert it to that. Okay. Yeah, that's the right way to do it. So what I would find is I would take my 2, I'll take my 3,000 times 500 times 60, and I divide it by 1e6, boom, and then I would take that, erase it to that. I don't buy it. Yeah. That's what I'm saying based on this right here. Let me go back and try it again. All right. So this one seems to me to be the regular, the one we're used to. It is a rating that has the standard life. This has a weird one. So I'm going to try to decide whether this is on the numerator or this is in the denominator. Yeah, that's what I did right here. I got it flipped. What I should have done was to say, if the catalog is right here. Okay, let me just go this way right here. FLA is equal to FLA. So if this is A, and this is B and B, right here. Let's turn this one into, what is it in terms of B, right there. So that this is probably, this was me trying to do it too quickly. This is going back to basics right here, and the basics. So if you were to say that you had, 2.0, that's the catalog rating right here, times, I said before that this messes me up. This is going to be the, I should have gotten this number, 3,560 to the third equals, here is the, I'll call it C, no, I'll call it, A with respect to B. We're doing it in terms of B. So that's going to be the 1 million raised to the third. Yeah. See, that's why I got it upside down. The one that I just decided to call A with respect to B. That means this is A in terms of B, and that's why I would have the thing flipped. So 3,000 times 560 times, and raise it to the third, and multiply it by, nope, somebody got it wrong. Oh yeah, I got it. Okay, that's why. I was right. That's just gets an absurd number. Yeah. Times 2, and then you take 1e6. Son of a gun. Is this to the... Oh, it's the F that gets there. There they go. Damn. Sorry about that. Right. 8.9. So you get 8.9 kilonewtons. And what that says is that this can handle more than that. Because I turned this 2 into the same basis as that. And like I said in the beginning, there's several different ways of rationalizing your way out. I don't like that problem, but maybe I should have started it. But it hit me as like, yeah, I remember that one. This seemingly easy problem can waste some of your time. That didn't make any kind of sense to me, that 0.463. That was way too small compared to that 7. And that led me to believe, like, I think I'm doing something wrong here. I better take a step back and look into that. All right. No, we shouldn't look at that problem. A basic problem in bearings is like one that's from the table in here. Like you wanted to try to pick a bearing for the bearing specifications given in the table, or you go down to one over here. Does it have an? I won't be asking a radial axial load one. That just takes too long to do the iterations. Although I have seen people who ask that question. Let's just do a basic bearing problem. One of these. Maybe problem 1113. Where we have for the bearing application specification given in the table for the assigned problem, determine the basic life rating for a ball bearing with which to enter a bearing catalog in table 11.6. Assume an application factor of 1. Okay, so we're getting information. We have to convert the radial load. So the F here is going to be 650 pounds. The life we're going to have is 5 years, which 40 hours per week. Seems like familiar. Did we do this one already? 400 RPM. And R is 95%. And they didn't quite say if that reliability was the entire thing or each bearing. Let's assume it's each bearing. But it could be the entire machine, in which case you'd need a reliability that was the square root of 95. Because each bearing would therefore, could possibly fail. So that if you want the machine to be 95% reliability, you need each bearing to be much more reliable than that. So here we'll start with just close that. Do that. I'm sorry. All right. So if you want to find kilonewtons, so right here we want a newton. We multiply the pound by 4.45. So this is 650 by 4.45. It's actually 448, but that's all right. and get it into newtons. So 2,893 newtons, so 2.893 kilonewtons. And try to flip back to this quickly if we can. Nope, apparently not. We want to get to this main equation right here, C10 AF FD. I'm going to write it like this right here. I'm going to go XD over reliability factor and 1 over A. And that reliability factor we should use from a table. Let's see if I have it. I don't want to flip too much, but there we go. Right away. Here is the reliability factor that we would get if we had 95. Oh, look, I already did it. I'm estimating that to be 0.62 is my reliability factor. So they told us this was 1. Oh, excuse me. Sorry. 0.62 from graph.
Assuming it's a graph you'll give us?
Yes, that's a graph I'll give you. It just seems ridiculous to make you go through that equation. What is the purpose of it? Except maybe just to reinforce that it's a Weibull as opposed to a Gaussian based thing. I guess, I don't know. So anyway, C10 application factor of 1, they told us 2.893. Oh, I needed to do that XD. I'm going to do it up here somewhere. XD is, as you'll remember, it's LD divided by LR. So you're going to get, we need hours. So 5 years by 40 hours per week, but we need 52 weeks per year. And those are hours, so we need 60, and the RPM is 400. And rated, we've decided, is manufacturer 2, which we pretty much always using manufacturer 2 at 1 million. So we got 5, 40, 52, 60, and then RPM is 400. So we get 249 million divided by a million is 249.6 for the life ratio. And so 249.6 divided by 0.62 raised to the 1 over 3. And I get 21.36 kilonewtons. I have this feeling we did this problem in class. I get a weird type of deja vu thing going on here. If it's 35 millimeters, I think we've done this problem before. Yes. So they say deep groove or angular contact. I think it doesn't matter in this case right here. Yeah, so like either way, whether it was deep groove and 35 millimeters would be the right choice. Because 19.5 isn't enough since we had 21.36. We need to pick 25.5, and so a 35 millimeter. Or if we want angular contact, it as well is at 27. I accidentally picked the same problem. That was totally random, by the way. But I think that was really good. Like I even picked my college randomly. Like there was no like desire. Oh boy, I want to go work on ships. I got in. Like why? The first week of school, the first week of basic training kind of thing, they're yelling at you, like, "Why did you come to school here?" I got in. It was free. That was the worst answer you could say. It was free. It was free. So I couldn't pay room and board at Georgia Tech. I got into Georgia Tech for a Navy ROTC scholarship, but it didn't. It was tuition, but not room and board. And I'm like, how am I going to do that? I can't. I mean, and back then, room and board was almost as much as tuition. It's like more than tuition, and you couldn't get a. That's actually not terrible. You couldn't. Semester or first semester? It was almost like it was close to that then. It was weird. I don't know how, but yeah. Anyway, we're done. I think. I'm sorry about the hiccups. Hopefully, you'll feel more prepared. No.
The 370 problem, should I be concerned about like SN diagrams, more circle, and all that?
I don't think more circle, but I think an SN diagram. Trying to navigate through an SI diagram.
Like a shaft problem.
I would more along the lines of like saying, like, you know, I think one of the problems. Let me see. One of the 370 problems that's in there. I took something like this right there, and I had this amount, and I gave you all the SE, like, and all the things that are done right there, and I'm just going to say, okay, well, you know, all you had to do is find the stress concentration onto this right here, and then like estimate the life, and I said estimate the life with the graph, so it was like, don't go through the calculation to the thing, like. I might even told you what the stress concentration was, or at least gave you what the Q was, or gave you what the notch sensitivity was. So you didn't have to look. I tried to find ways to make it so that it was, you know, if it's a 75-minute exam, and there's 4 divided by 4, right? I should know if that's like 75 divide. That should be 18.75 minutes per problem. And for me, I should be able to do that in 9.4 minutes. Right? So I tried to figure out a way that it was like, obviously I already know how to do it. So that's an aspect. So I tried to also slow myself down by flipping through the book and finding the thing that I need to find and pretending I don't know what the equation is and all that kind of thing. But like the big idea that I want you to be able to remember to do is be able to, right here, we've been able to estimate the life of something. Right? Because I think it's something that I would like you to retain from ME470. Or if there was a non-life one, it'll probably be something where you would need to use, you know, von Mises, because I want you to retain a von Mises thing, but not trying to trick, just trying to
pull it back from you. And I know this is maybe not a mindset that I'm going to be honest, though. Like, I think people learn things from exams, relearn things from exams. I measure your mastery of the thing, and that's my main goal, but it's also like I want to rejuvenate those things. So when you get out to that first job and you're given a task to do something that could potentially be relevant to what we have in class, that you're able to like pull it back. And I think people relearn things all the time. You forget, things get displaced, but then you rejuvenate, and the more times that happens, the more likelihood it is to stick. So, anyway, thank you for your patience. Oh.